In this lecture, we shall discuss about angular momentum and the commutation relations among different components of angular momentum. And if we get time, then we shall discuss about the rigid rotor. Okay, so first angular momentum. First we discuss orbital angular momentum and the commutation relations. We know from classical mechanics that if r is the position of a particle, let us say the system consists of a single particle for the moment, and if the linear momentum is a small p vector, then the angular momentum is defined by this. This is the position vector, and this is linear momentum. This is a vector quantity. We consider a single particle. And this is angular momentum. Now, from the cross product of r and p, L can be written as unit vector along x direction, unit vector along y direction, and unit vector along z direction. And the components of r are x, y, and z. And the component of the linear momentum are px, py, and pz. So this from this determinant we have this ypz minus zpy, and this is zpx minus xpz, and then this is xpy minus ypx. Therefore, we can write down the components of Lx is equal to ypz minus zpy, Ly is px minus xpz, and Lz equal to xpy minus ypx. So these are the components of the angular momentum vector L. Now, since the momentum vector, it has the operator is minus I a square del, where a square is nothing but the Planck's constant divided by 2 pi. Okay, so in terms of this, we can then show that the different components of the angular momentum, they can be represented by operators according to the second postulate of quantum theory, that Lx is nothing but minus I square. This is y del by del z minus z del by del y, and Ly minus I h cut is z del by del x minus x del by del z, and then Lz minus I h cut x del by del y minus y by del x here. So these are the operator form of the components of the angular momentum. Now, if we assume x is, this is 1 and y 2, z 3, that is by taking x1 equal to x, x2 equal to y, and x3 equal to z. We can write L I. Okay, let us say instead of operators, we just the variables, the physical observables. Li can be written as epsilon I j k and x j and p k, where there is a summation here, and the the quantity here epsilon I j k this is, it can have three values, is +1 if cyclic order in 1 2 3, and this is -1 not in cyclic order, not in cyclic order in 1 2 3, and if any two indices are same among I j k, then it will be 0. If two of the indices are same, then actually this one can be reduced to these relations. Now we have L square equal to Lx square plus Ly square plus Lz square, and also if we consider spherical coordinate system, because later on we will see that angular momentum is related to the angular variables of the coordinate system. So if we have then also if we consider a spherical coordinate system method, then the relation between Cartesian coordinate system to the spherical coordinate system will be this. We know this actually from x, y, z to move to r theta phi, where r is the radial coordinate theta and phi, and I'll show you the figure that the coordinates x, y, z and r theta phi. This is x direction, say this is y direction, and this is z direction. Now if a point here P whose coordinate is r theta phi and also x, y, z in Cartesian coordinate geometry, then if we add this will be the radial coordinate, and if we draw a perpendicular on the xy plane, then this this is the x direction unit vector, and this is the unit vector along y direction, this is the unit vector along z direction, and this is Pn and this is M. Then this is x, this is y, and this angle is theta, and if we add this with the the origin, then this angle is phi, and the relations are this: x is equal to, it can be shown that this x equal to r sine theta cos phi, y equal to r sine theta sine phi, and z equal to r cos theta. So you see, if we know r theta phi, the coordinate of a point, then we can calculate the coordinates x, y, z in Cartesian coordinate geometry. And similarly, if we know x, y, z, then we can calculate r theta phi from these relations. If we square these equations and add, then you will see that r is equal to the square root of x square plus y square plus z square. Easy to show. And if we divide this one by r there, and then theta will be given by this cos inverse this z divided by r. R means x square plus y square plus z square to the power 1/2. Similarly, if we divide this equation by this, then we'll have tan phi equal to y by x. So phi will be given by tan inverse y by x. So you see, if we know x, y, z, the coordinates of a point in Cartesian geometry, then we can calculate the coordinates r, theta, phi in spherical polar coordinates geometry. Now, if we do some mathematical calculations, some algebra, and some calculus, and then it can be shown that the x component of the angular momentum is nothing but, in terms of r, theta, phi, is this I cut and sine phi del by del theta plus cot theta cos phi and del by del phi. So you see there is no dependency on r, the radial coordinate. Similarly, Ly operator, y component of the angular momentum operator will be minus I cut, and this is cos phi del by del theta and minus cot theta sine phi del by del phi. And Lz, this is the z component of the angular momentum, and which is just minus I cut del by del phi. This you can show. Now, if we square this, okay, these three expressions, if we square them and add them, then we will find the L square operator from this equation, and it can be shown that then that L square operator will be equal to minus a cut square, and this is 1 by sine theta and del by del theta. These are partial derivatives, and here sine theta del by del theta and plus 1 by sine square theta del square by del phi square. We also know that the operator del square in spherical polar geometry is 1 by r square del by del r square del by del r, and here 1 by r square sine theta del by del theta sine theta del by del theta and plus 1 by r square sine square theta del square by del phi square. Okay, now this expression of del square now can be written in terms of operator L square. And del square is written as 1 by r square del by del r square del by del r, and this is minus L operator square by square r square. So you see the del square operator can be written in terms of angular momentum operator square this way. Now we shall discuss some commutation relations among the different components of the angular momentum operator. commutation relations for orbital. L actually is known as orbital angular momentum. These are the commutation relations. We can prove this. This is not unit vector. Remember, this is the operator x. This is operator y. Operator z. And this is equal to 0. This is 1. Second, Lx y equal to I squared z. Ly z x Lz x I squared y. This is Lyx. This is equal to minus I squared z. This is if Lzy I squared x and Lxz minus I squared y. Fourth, Lx commutator of Lx Ly is I squared Lz. Similarly, Ly Lz I squared Lx. Lz Lx I squared Ly. Okay. 5. L square Lx equal to L square Ly L square Lz, the commutator, all these are 0. 6. Lx Py this is I squared Pz. Similarly, Ly Pz I squared Px. Lz Px I squared Py. But if we take here Ly and here Px, then it will be minus I squared Pz, and similarly this. And another one, if this is say Lx and here Px, then this equal to Ly Py Lz Pz give you 0. This can be shown. Okay, we'll show only one. Okay, let us prove this one. So rule 5. That means L square Lx should be 0. Let us see what happened. Left side L square Lx, and this is, L square is Lx square plus Ly square plus Lz square, and here Lx. And this one can be written as Lx square Lx plus Ly square Lx plus Lz square Lx. But this one is 0 because Lx cube minus Ls cube, so is 0. And this one we write down Ly Lx, and similarly this one Lz here Lx. Now this one can be written as Ly and here Ly Lx plus Ly Lx here Ly plus this one also Lz here Lz Lx plus Lz Lx and here Lz. Okay, this then we have written from using this rule that if we have a commutator like this, then this is plus okay, this is a formula. So we have used this formula. Now you see this this one is Ly, and this is nothing but minus I squared. This is not in cyclic order, this is in anti-clockwise. No, it is clockwise, y and then x, so we have minus sign, and it is Lz. Similarly here minus I squared Lx um, this is y, so not lx, this is lz here, this is y in x, so lz, and we have ly. Okay, and plus lz, and this is z and x, so is I cut ly, so is I cut ly, and we have lz. So you see this minus I cut ly lz minus I cut lz ly, and we have I cut lz ly and I cut ly lz. So you can cancel all this, and which gives you 0 equal to the right hand side. Similarly, you can show all the other commutation rules. Okay, we do not have time today, and we would like to stop here. In the next lecture, we shall discuss about the rigid rotor, and if we get time, then we shall discuss about hydrogen-like atoms.